Oftentimes, half-life problems will involve scenarios where the half-life decay is outside of a proportional progression over the function of time. One such example is radioactive cesium-134 has a half-life of 2.06 years. A hazardous materials HAZMAT crew is prohibited from storing more than 10.0 kilograms radioactive cesium-134 per cubic meter after a 5-year time period. Calculate the maximum initial kilogram mass quantity of radioactive cesium-134 permissible upon initial storage per cubic meter. Calculate the following HAZMAT storage half-life values if maximum initial cesium-134 mass is selected. Part A, remaining kilogram mass cesium-134 per cubic meter after 3.75 years, and B, remaining kilogram mass cesium-134 per cubic meter after 5.00 years. Establish an equation given HAZMAT crew can use to calculate half-life, radioactive decay in kilogram mass per cubic meter over a 5-year time period that is compliant with specified legal storage limit. So for answer 1, the first step is to compute the percent decay per year, for which we can stick with percent value 50% half-life divided into the half-life time 2.06 years, which equals a decay rate of 24.27% per year for the given material cesium-134. The time limit specified 0 to 5 years, or greater than or equal to 0, and less than or equal to 5. So we select t is equal to 5 as the maximum time limit. We then use the exponential function e to the negative kt power, in this case because it's a decay function. We select some abbreviated output, final value, in this case c, to represent cesium-134, and then the initial value, the c lowercase o, or c aught, is the initial value times e to the negative kt power. So when we incorporate the k constant, this will simply be the decay rate in percentage expressed as in decimal form, so negative 0.2427 t. So we need to solve for the initial value to compute the maximum initial quantity of cesium-134. So we can then specify 10 as the output. The input is unknown, c aught, or initial value of cesium-134, times e to the negative 0.227 t. We then algebraically solve for c aught by rearranging 10 divided into c aught, or initial value, is equal to e to the negative 0.2427 times a 5-year time limit. So when we compute the e to the negative 0.227, e to the negative 0.2427 times 5, we come out with this value here, which is equal to 10 over the initial value. So when we solve for the initial value, we compute a maximum initial quantity of cesium-134 to equal no greater than 33.65 kilograms. So we can then check the work by inputting 5 years for time, and we do indeed calculate 10. So 33.65 kilograms maximum initial radioactive cesium-134 is permissible? Answer 2, we simply set up the initial value times e to the negative 0.2427 times the time involved, so 3.75 years. So 13.54 kilograms mass radioactive cesium-134 is specified as the remaining kilogram mass cesium-134 per cubic meter after 3.75 years, so it's still within the legal limit. After 5 years, we cannot exceed 10. So part B of answer 2, we input 5 years and for time, and we do indeed calculate 10 kilograms of mass radioactive cesium-134, thus also legal. And then question 3 is the equation the HAZMAT crew can use to calculate half-life within legal limits, and it would be this equation here. C is equal to 33.65 e to the negative 0.2427 t. T can be substituted with x in your graphing calculator, so if you would prefer to view the limits and output graphically, you can do so as well. As for doubling time, a calculation often made with respect to nonlinear rate of increase, we can take the example. In 1920, a certain city's population was recorded as 34,000 people. By the end of 2020, the city's population was recorded as 380,000 people. Write an equation that describes the population growth of the city. Calculate the population doubling time of the city in years. So the first step is to calculate the time difference of the time period. So 2020 minus 1920 is 100 years, so t is equal to 100. We then implement the exponential e to the kt function by designating the output capital P to equal the final population of 380,000 people to equal the initial P aught population of 34,000 people to e or times e to the positive kt power as denoting increase. So therefore P is equal to 34,000 e to the kt power. So we simply solve for the constant by dividing and rearranging the final population divided into the initial population to equal e to the 100k. We can substitute the t before the k for simplicity's sake. So therefore we need to cancel the exponential value here by applying the natural log to the value. So therefore what we do to one side we also do to the other side of the equation. So natural log of the ratio of the final population divided into the initial population will equal the natural log of e to the 100k power. So when we solve for the natural log of the final population divided into the initial population, we get this value here, and then natural log multiplied times the e, they cancel out, and we're left with 100k. So now we have a pretty simple algebraic expression to solve for to calculate k, the constant. And when doing so, we calculate this value here for the constant. So our equation to describe the population growth of a city is specified here, boxed in blue. Again, you could substitute the t with x if you prefer to put this in your graphing calculator to graphically ascertain output values over the function of time. So therefore we have calculated the k constant, which means that the doubling time is equal to the natural log of 2 divided into the constant, or 28.7 years is the doubling time, which equals 28 years, 8 months, and 12 days. So the doubling time in years for this given city is approximately 29 years. Thanks for watching this video, and have a great day.